Hi, welcome to this lecture of CSE351, which is Introduction to Data Science, and this chapter is on mathematical preliminaries. So here we will make some foundation for the basic probability and statistics which we need for data science. And let me start with one of the sentence of our textbook, the Data Science Design Manual. It's somewhere in the beginning of this chapter, which is chapter number 2. And it says that you must walk before you run. So let's make an attempt to walk. Let's warm up a little bit, and by doing that we'll gain some confidence, and that will help. Okay, data science, since it will have some elements of machine learning, so we will need some foundation in probability and statistics. So let's see, let's brush up the concepts that we may already have, or if not, then we will build. About probability. So probability and statistics, these are very important in data science, and they are used together most of the time, and it's often confused. So let's try to understand the difference between probability and statistics. So we will start with probability. Like, what is probability? So let me start with this definition here that says that probability theory provides a framework for reasoning about the likelihood of events. So the point is, where exactly we should be using probability. So we will use probability in prediction models. So a lot of predictions that we will be making would be based on probability. So we will use probability whenever we have to make some guess about future, when we have to make some reasoning about some event which has to happen in the future. So that's what we mean about this thing, that it's a formal framework for reasoning about the likelihood of an event. Okay, so that's what probability is. So now when we talk about probability, then there are some terms that we should be familiar with. So let's start looking at each term one by one, and we will have some examples, and those examples will help us understand these things. So what is an experiment? Probability would be based on some experiment that we are doing. So what would be an experiment in the discussion on probability? Experiment is a procedure which yields one of the set of possible outcomes. So in this example, we have the example of tossing two six-sided dice. So this is slightly complicated case, but let me give you a very simple experiment idea. So the experiment could be as simple as tossing just one coin. So if you're tossing one coin, then it may result in head or tail. So that's one experiment involving just one coin. You can toss two coins, and that's the experiment number 2. You can have experiment number 3, where you have a 6-faced dice and you're rolling it. And when you roll it, the result would be the face that shows up, and you will notice the number that shows up on the face. So that's another experiment. Now the experiment that we will be discussing in this chapter is slightly complicated, which involves tossing of two six-sided dice. Okay, so what would be the outcome? We will discuss about that. What is the sample space and all, we'll discuss that. So the probability and experiment, these two terms should be clear to you by now. Okay, so now what is the sample space? So whenever you do an experiment, then whatever possibilities you can have as the result of the experiment is conceptualized in sample space. So for this problem that we have, which is slightly complicated, let's think about the sample space. So here we have two dice, and each dice has 6 faces. Now to make the things easier to understand, let's think that we have the two dice that we have are of different color. One is red color, the first one is of red color, and the second one is blue color. So each dice has 6 faces, so the number of cases possible is 6 multiplied by 6. On the first dice, you have 6 faces, each marked with number 1, 2, 3, 4, 5, and 6. And similarly, same is the case with the second dice. So now, what is the sample space? So the sample space is right here. Let's try to understand what do we have here. So 1, 1 means that when you roll the 2 dice, you got 1 on the dice 1 and 1 on the dice 2. So here the reason why you see these numbers with different color is that the number that you see as red, that means it's the result of the rolling of the red dice. Whereas the second part that you see in the parenthesis, which is in blue, is the result of the second dice that you had rolled. So when you're rolling the dice, there's a number showing up on its top face, and that's the number which we consider. So let's see what are the different possibilities. You can have 1 1 on each dice, or you can have 1 on the first one, 2 in the second, so on and so forth. So in the first row you have the combination of 1 on the red dice and the different numbers on the blue dice. So 1 1 1 2 and so on till 1 6. So these are 6 possibilities with 1 on the dice with color red. Now let's think about the other scenario where the first dice, which is red in color, is showing up number 1 on the top. You can have with 2 on the top for the red dice, you can have these 6 combinations: 2 1 2 2 2 3 2 4 2 5 2 6. So you can reason this way and you'll come up with this sample space. So this sample space has all the possibilities, all the possible cases that might arise when you are rolling these 2 dice. With 6 faces, one being red, the other one being blue. Great, so that's the sample space. Now, if you really want to understand sample space and you want more examples from me, then I'll say that let's look at a very simple case where you have just one coin that you're tossing. Now I would ask, what is your sample space there? So the answer to that is very simple. H for the result being head, T for the result being tail. So the sample space for tossing a coin will have just 2 outcomes: H when the result is a head, T when the result is a tail. Similarly, if I say that you just have one dice that you are rolling, then what's the sample space? Well, you should say, now my sample space will have only 6 elements: number 1, number 2, number 3, 4, 5, and 6. So these are 6 elements. Okay, so I hope what I'm telling you is making sense. Now when you have sample space, then there's something called as event. So event is something we are interested in, and we want to find out the probability of that event being happening. So this event is also slightly complicated, and all these things we are doing with an assumption that you have some background in probability, and the purpose right now is to brush up your concepts of probability. So what's the event which is of our interest? So we are saying that the event is such that when you toss those 2 dice, then the sum of the number that shows up on the result of this experiment is either equal to 7 or is 11. So there are 2 conditions. So we are considering 2 outcomes in our event. So what are these 2 outcomes? Outcome number 1 is that the sum of the numbers that shows up on the top of each dice adds up to 7. And the other output 2, is that the sum of these 2 numbers that show up is 11. Okay, so now you should see that in E, which is a set again, I'm considering all the favorable cases which are there in my event. So if you pay attention, then I have two sections here, one which is highlighted with yellow and the other subset which is highlighted in blue. So why do I have these two different highlightings? Because pay attention to these numbers that I have in the parentheses. 1 6, that is, if you add it is 7, 2 5 is 7, 3 4 is 7, 4 3 is 7, 5 2 7 6 1 7. So these are the 6 cases, 1 2 3 4 5 6. These are the 6 cases which will result in the outcome where the sum of the number is 7. We can call that as outcome 1. Whereas these two cases, 5 6 and 6 5, are the two cases that corresponds to the outcome 2, where the sum of these two numbers which are showing up on the top of the on the top face of the dice is adding up to 11. So that's our event, comprising of two outcomes. Outcome 1 where the sum is 7, outcome 2 where the sum is 11. Good, let's move on. Alright, now what is probability? So how do we compute probability? Well, I'll make an assumption that you already know how to compute probability, but in this exercise I'll kind of give you an idea how to compute the probability. But what is probability? So given for any for any outcome like S, if you have to compute its probability of an outcome S, then the value that you get for the probability has to be in between 0 and 1. It's never negative and it's never more than 1. Okay, so if you have an outcome and for that outcome you want to compute a probability, then meaningful probability will always be in the range from 0 to 1. It could be 0 or it could be 1, or anywhere in between 0 and 1. It never goes below 0 and never above 1. Good, that's one thing. And how about the second condition here? The second condition says that when you add the probability of all the possible outcomes, then the result has to be 1. Okay, so if you add all the probabilities of all the possible outcomes of your sample space, the result should be 1. So these are very important conditions related with probability. Alright, so now we are making some foundation so that we could solve or we could compute the probability for an event that we had in the previous slide. Now what is the probability of an event? So assuming that our event has more than one outcomes, as we have in the previous example, then how should we find out the probability of an event which has more than one outcome? So the probability of an event E is equal to sum of the probability of each outcomes. Okay, so PE, which is the probability of the event, is equal to, this is the summation sign, that means you have to add what? The probability of each output. What do you mean by S belongs to S? That means if S is the sample space, right? Now we are interested in only S that belongs to the event. Okay, I believe it should be S belongs to E. So there is a typo. There's a typo here. I will double check and I will make an announcement and I'll update the slide. I have a strong feeling that S should belong to E. Seems like a typo. Sorry about that. Okay, so the outcomes that we have should be those outcomes that belong to our event set. So now let's apply all these things that we have learned till now to this example, which says that event is given to us, and this event has two outcomes. Outcome 1, where the sum of the numbers showing up on the top of each top of the face of the dice adds up to 7, or that adds up to 11. So we have S1 and S2. So the probability that we have to compute here, let me use a pen. I believe that will make it a lot better, and I will use the blue ink. So what should I do here? Let me, alright, sorry about that. I will call it S1. That is the outcome 1, and this is S2. Alright, so I have S1 and S2, and okay, so right here, so here as I said, it should be an E. S belongs to E, and in E, the example that we have for E is S1 and S2. So the probability that we are computing here should be the sum of the probability of the output S1 and the probability of S2. And what is the probability of S1? So we will go back and we'll make sure that this is making sense. This is probability of S1, and right here you have probability of S2 outcome 1 and outcome 2. So how many cases do we have for S1 in favor of S1, which is the sum being 7? 1, 2, 3, 4, 5, 6. Therefore, the first term that you see here is 6 by 36. And how about outcome S2? There are 2 cases. Alright, so that is 2 by 36, which is 8 by 36, and the probability of the event E is 2 by 9. So please work on these things. I have the assumption that these things are simple. If not, please let me know. Okay, so now let's move on and let's learn about another term which I believe might be new to you, but this is very interesting. This is the concept of random variable. So what is a random variable? Okay, so this random variable is slightly different from the variables that you might have seen in your algebra. So this random variable has to do with probability. Now, why do we need a random variable? Random variable is a mapping that maps the outcome of some random processes to number. Okay, so that's one way of putting the definition that we have right here. So let me do this thing. Let me read the definition, and then I'll give you some alternative definitions to explain that. So here we are saying that a random variable V, so random variables are usually denoted by capital letters. So that's the reason we are calling that as capital V. So random variable is a numerical function on the outcomes of probability space, and the example of that could be the function's sum of the value of 2 dice. So let's not go to the example. Let's first try to understand the definition. So the purpose of a random variable is to map the outcomes of the random events or random process to some number, and then deal with those numbers. Okay, so that's what we are trying to say here. That a random variable V is a numerical function on the outcome of probability space. Okay, so let's try to understand that from the example that we have here. So The example that we are dealing with involves a pair of dice. We have two dice, one red, the other being blue. We are throwing that. We are rolling these two together. Now we have seen the sample space. The sample space has the 36 different possibilities. Now what's our random variable in this experiment? So the random variable that we have right here, which we are saying as VAB, we are defining it as A plus B. What is A here? What is B here? A is the number that shows up on the top face of the red dice, whereas B is the number that shows up on the top face of the dice in blue color. A for red color dice, B is for the blue color dice. And what we are doing, we are adding these two numbers. Alright, so now if I say that with this function applied, why are we applying this function? The function is adding up the values that is being shown up on the top of the two dice. And why are we applying this function? Because we want to map the outcomes to some value. Okay, and now you should ask, like, why are we doing this exercise? The answer to that is, it makes our life a lot easier. It makes it very convenient to discuss the probability, and more details on the probability or more in-depth study of the probability revolves around the concept of random variables. Okay, now, so if you follow that thing, then let's try to identify what are the different values that we will get for the random variable V that we just defined. VAB is equal to A plus B. So now, since it involves adding up of the number which is showing on the top face of the two dice, then you should agree with me that the minimum value that you will see when you have rolled two dice is 1 plus 1, where number 1 is showing up on both the dice. So in that case, the smallest value would be 2. And similarly, you can reason the same way. And if I ask you, what's the maximum value that you're expecting in this experiment, then you should say that, the max that I'll get is when 6 is there on the face of the red dice, and similarly I have another 6 on the blue dice. So when you add these two numbers, 6 plus 6, then the maximum value that you get is 12. So what did we do? Well, with the help of this random variable V, which we are defining as the sum of the value of the two dice, with this random variable, we are able to map the outcomes to these numbers. Okay, good. Now, if you understood this discussion, then let's move on and see, like, if you have defined a random variable, then how can we use random variables for the discussion on probability? Alright, so let's look at these two cases. What are we saying here? We are saying that what is the probability where the result of the outcome, right? S is an outcome. We don't know what is that outcome, but we know that the value is 7. So what does that mean? That means the sum of the two numbers is 7. Alright, now you have to find out the probability of those cases where the sum of the number that shows up on the dice is 7. Okay, so that's what this is so concise. If you want, you can write that in English also. But once you have defined your random variable using this function, which is kind of mapping the outcome to numbers, the number is 7 here. Okay, so it's so convenient. And if you want to understand what are these outcomes, what are the different outcomes that I should consider, so being 7 means you will have 1 and 6, then 2 and 5, 1 6 2 5, and then 3 4 and 4 3. All these are adding up to 7. Then you should have 5 2 6 and 1. These are 1 2 3 4 5 and 6. So 6 divided by 36, which is 1 by 6. Alright, good. So similarly, if you have to find out what is the probability when my random variable v is taking the value 12, when can that happen? Only when you have 6 and 6, right? We don't have any other combination which will give you 12. So the reason the probability would be 1 by 36. Alright, so I hope you got these concepts. If not, please let me know. These things are important, fundamental, right? But if you can't follow anyway, don't give up, right? Because there are still a lot of interesting things that you will get without following these things 100%. But please give it a try. Give it a try, please, and let us know, me and my TAs. You'll know about my TAs pretty soon. Okay, great. Now there's one point here that I need to explain. When you have this notion of random variables, then using that, you can define something called as probability distribution. What does that mean? Well, right here, if you're looking at, then you see some numbers. 2, there should be 1 3 right here. 2 3 4, we have 5 6 7 8 9 10 11 and 12. So these values that you see on the x-axis, it corresponds to the value that your random variable can take, right? So from here, if you see, your random variable v can take the value from 2 to 12. So that's the reason you see from 2 to 12. Now what are we showing on the y-axis? On the y-axis, we are showing the probability of the random variable taking a particular value. So what's the probability of random variable v taking the value 2? And when will it take the value 2? It will take the value 2 only when you have 1 and 1. Alright, and what's the probability? 1 by 36. Alright, so that's the value you got right here. Okay, now what value do you have here for 3? When v is equal to 3, when can that happen? V is equal to 3 will happen when you have 1 2 and 2 1. If you find out the probability of v, then probability of v is equal to 3 will be equal to 2 by 36. Alright, and go on finding it, and you will realize that when the value is 6, alright, when the value is 6 and also 7, you have the highest probability. And then when the v takes on value 8, it goes down. With 7, it goes down further. Alright, 8. With 9, it goes down further. And with 10, it goes down further. And with 12, it's the same probability as you had with, what is it? With 2. Alright, great. So I hope that this discussion is making some sense. Let's move on. Now we have reached to a point where we will discuss the difference between the probability and statistics. Okay, so the probability is a theoretical part of mathematics, right? So as we have already seen, that a probability will deal with the predictions that we'll be making about a future event, and it is a theoretical branch of mathematics. Whereas in statistics, we only work with the data that we have from the past. In probability, we try to predict the future events, whereas in statistics, we work on previous data that we have, and using the previous data, we come up with some conclusion. Whereas in case of probability, we predict the future. But interestingly, in probability as well as statistics, we somehow deal with the relative frequencies of different events. Okay, but the focus is different, slightly different. In probability, our focus would be in predicting some event of future. All right, whereas in statistics, we analyze the historical data or previous data, and we try to reason with the previous data. Probability is a theoretical branch of mathematics, whereas statistics is an applied branch of mathematics. Okay, so that's another difference. It's good if you remember these things, because often we confuse with probability and statistics, and that is very, very common. Even the experts, they do it. Alright, so now let's move on with the probability and try to understand this concept of independence. So let's look at this independence compound event, and I'll explain this thing further in the next slide. Now let's take this example. Okay, so this example is interesting from our textbook. So let's think of two events. Event 1 is based on the fact that half of the students in the class are female. So the probability of A would be 1 by 2, 50%, right? Because half of the students are female, the remaining half are male students. Now there's another event, which is event B. So the event B is that if you pick a student, then the student is above average in the performance, right? So now again we are making an assumption that we have an ideal situation. Ideal situation in the sense that half of the students are male, the remaining half are female. And the event B is, or the fact B is that the half of the students are above average and half of the students are below average. So this is not median. In the median, you will have 50% above, 50% below by nature. But in the average, that may not be the case. But in this case, we have 50% students above and 50% students below. Now, if we make this assumption that these two events are totally independent of each other, right? The student being above average or below average has to do nothing with the gender of the student. Then if somebody is asking me that what is the probability that if you pick a student and that student happen to be above average and female student, okay, so now if these two cases are independent of each other, then this computation is very easy for me. Why? Because the independent event probability follows a simple rule. What does it say? It says that when you're trying to find out the probability of A intersection B, which means happening A as well as happening B. What is A here? Event being a female student. What is B here? Event being that female student is above average. Now these two events are independent. Let's assume that, and most often that is the case, right? The intelligence has to do nothing with the gender. So what would be the probability that you pick a student and student happens to be a female and above average? So that will be the probability of the student being female and the probability of the student being above average. So let me use pen here, and I change the color as usual. So here, what is PA? Now let me put that right here. Is equal to 1 by 2 is equal to 1 by 2. So here PA is equal to 1 by 2, PP is equal to 1 by 2. So the result is 1 by 4. Alright, so there's this interesting fact about independence. There's a community that loves independence, and there's another community that doesn't like independence. Okay, so if you're talking to somebody who's doing probability, right, an expert in probability, whose work is mostly around probability, that guy would love to see this independence condition, where two events have no correlation between each other, like this case. So the probability person would be very happy with the situation. But unfortunately, people like us, those who are doing data science or machine learning, data analytics, they would like to have some dependence between the events. They would love to find some correlation between the events, because if they find some correlation, then using that correlation, prediction or forecasting of a future event becomes a lot easier from the knowledge of some event that has already happened. Okay, so just to give you some idea on this thing itself. So when we are saying that, it's bad for prediction, right? Okay, so bad for prediction. This is something I want to highlight. And let me give you some example from the data science domain. So from the data science domain, let's think of this task where we have to predict. We are predicting predict the mail or email as spam. That's a very common, very common and an interesting problem in machine learning and as well as in data science. How do you predict whether an email is spam or not? So let's say that the prediction of the email that we are doing is the event B. We want to find out the probability that it is a spam. So that event is B. And now if we find some and that's the event B, which is finding out whether the email is spam or not, is an event B. And let's think of an event A. So event A deals with some distribution of words, in the email, words, because email will have words, right? So this might be a little technical for you right now, but don't worry, just get some idea about it. We have two events, event B, that it's a spam, and A, that has to deal with the email contents, the distribution of the words. Now if there is some correlation between the words in the email and the fact that it is spam or not, then that is a good news, right? And you'll agree with me that spam emails have specific words, right? So yes, that's a good news. We have some correlation between the distribution of the words and the fact that it is being a spam. And if there was no correlation or no dependence, or if the events like B and A, B being spam and A being the word distribution, were independent of each other, then that's a bad news. Probably we'll have to look for something else, some other feature to predict whether a mail is spam or not. Alright, so let's see. And somehow I have this feeling that this lecture might be a little intense, but I'm happy that this is more objective than the ones that I had earlier, more subjective ones. But yeah, data science would be more objective, more problems. Okay, good. So now I have the same example repeated here for the reason that I want to tell you about the compound events. Alright, so the event that you're looking at right now is compound. But when you have compound event, I should also tell you about simple event. what is a simple event. When you understand a simple event, then understanding compound event would be easier. Now in simple event, we have a single output, outcome I should say, not outcome, single outcome. Example, you'll say, okay, give me an example. So if you have just one dice, alright, you have one dice and you are saying that for this one dice, what is the probability that you get the number 5 on the face. Okay, so there is just one dice that you are rolling and you'll get an output, and you can determine whether it is 5 or not, and you will have an output for that. So that's a simple event, just one outcome possible, either 5 or not 5. Similarly, you can think about a coin as well. You had one coin, you tossed it once, and it is head or tail, you'll get the output. That's a simple event. But right here you have a compound event. Why is this compound event? Because here we have more than one dice being rolled. Okay, and the events possible are whether it is equal to 7 or 11. So there are two events possible. There some can be even 7 or 11. Okay, it's just not one outcome, there are multiple outcomes possible. Now this same can be turned into a simple event when you have the output only as 6 and 6. That's just one possibility. Alright, so let's move on. Now we'll move on to another interesting concept on probability, which is called conditional probability. So when you have two events which are related with which are correlated, then the one event happening will give us more information about the other event happening. As an example, I gave you a slightly technical problem where you want to predict whether an email is spam or not. So if you have some correlation between some words in the email and the fact that it is being spam, then we can use the conditional probability. When we know that there are these words which will make it susceptible for spam, then yes, our prediction about spam would be better. Okay, so let's try to understand this conditional probability. What is this conditional probability? Now we will say, let's in order to discuss the conditional probability, let's think of two events, event A and event B, and they may or may not have any correlation or dependence, but let's think about computing the conditional probability of an event provided the other event has happened. So let's look at this representation. This is important. We'll say the conditional probability P A given B. So this is read as the conditional probability of A given B. When you have a pipe in between, we read that as, you can write as P parenthesis A pipe B, but it is read as conditional probability of A given B. Now how should we compute this, right? So let's learn these expressions because these are standard, and we'll be using these definitions to compute our conditional probability. Now how do you compute the probability of A, conditional probability of A given B? That means the event B has happened. Now what is the probability of A being happening? Alright, that's the conditional probability of A given B. So how do we compute that? We will find out the probability of A intersection B, that means the probability that the A and B both conditions are satisfied, divided by probability of B, right? So conditional probability of A given B is equal to the probability of A intersection B divided by the probability of B. Okay, now this conditional probability is only interesting for us as long as we have some dependencies between events, as long as the events are correlated somehow. Alright, well, this is interesting for us only when the events are not independent. Alright, because if the events are dependent, then we can write probability of A intersection B as probability of A into probability of B. So that's a condition about the independent events. So if A and B are two events which are independent of each other, then we can write probability of A intersection B as probability of A multiplied by probability of B. Right, so we could write this as probability of A multiplied by probability of B because A and B are independent. So if they are independent, we can write it as probability of A multiplied by probability of B. Then you have probability of B in the denominator. This cancels out. So probability of A, conditional probability of A given B is same as the probability of A. So the fact that you're telling, the information that you're getting after the event B has happened has nothing to do with A. Alright, so this fact that conditional probability of A given B is same as probability of A means that the event B happening has no impact on A. So A and B are independent events. Okay, so alright, let's move on to the next important topic on probability. This is Bayes' theorem. Now Bayes' theorem is again a very important and interesting theorem in probability. And what is the purpose of the Bayes' theorem? Well, it is used to reverse the direction of the dependence. What does it mean? Well, then look at the right hand side. So if I know the conditional probability of A given B, and I also know the probability of B and the probability of A, then I can compute the conditional probability of B given A. Okay, so one more time. Okay, so why is this Bayes' theorem important? This is an important tool because we will use it to reverse the direction of dependence. What's the direction? Well, you have the information, you have the value of, you have the conditional probability of A given B. If that information is available to you, then using the Bayes' theorem you can compute the conditional probability of B given A. How do you do that? Use this formula, which is conditional probability of B given A is equal to condition probability of A given B multiplied by B divided by probability of A. Well, probably this is difficult for you to remember, but I'll give you a trick, like what trick you should use to remember Bayes' theorem. That will come in the next slide. But just to make it interesting and just to make sure that we learned how to use Bayes' theorem, we will use these two events. We have two events. Event A says that at least one of the two dice that we are throwing should have even number on the face. So it is saying at least, right? So that means if you have both of the numbers as even, that is fine too, but at least one of the number which is showing up on these two dice that you're rolling should be an even number. Okay, and what's the even number B? Even number B we have already seen, which is the even that the sum of the two dice is either 7 or 11. Okay, good. So what should I do here? Okay, good. So let me tell you the trick, like how should you remember Bayes' theorem. So for Bayes' theorem, before that, let me tell you about how to write the probability of two events A intersection B. Right, so the probability of A intersection B is written as probability of A multiplied by probability of B, conditional probability of B given A. Okay, so probability of A intersection B is equal to probability of A multiplied by probability of B given A. And the same thing can also be written as the probability of A intersection B can also be written as probability of B multiplied by probability of A, condition probability of A given B. Alright, so the probability of intersection of two events A and B can be written as either probability of A multiplied by conditional probability of B given A, or probability of B multiplied by conditional probability of A given B. So now let's pay attention to these two terms. Alright, now if you want to know what is the probability of conditional probability of B given A, then let's work on these two parts. What I will do, I'll say probability of conditional probability of B given A is equal to probability of conditional probability of A given B, doesn't matter if I change the order, into probability of B divided by, I'll take this right here to the denominator, probability of A. Alright, is this the Bayes theorem that we have on the previous slide? Probability of A given B, probability B, yes. Alright, so it's not difficult. You don't need to memorize anything. If you remember this expression, which is quite intuitive, you can derive the Bayes theorem. And what we are doing here, we are just reversing the conditionals, right? So conditional probability of A given B is used to derive the conditional probability of B given A. Now there's another interesting thing actually. This is the case where you may have dependence. If you have, for independence case, right, if A and B are independent, then probability of A intersection B is equal to probability of A multiplied by probability of B given conditional probability of B given A. But since these are independent of each other, it will be same as probability of B. So what's the condition of independence of two events? The intersection of their probability of A intersection B is equal to probability of A multiplied by probability of B. Okay, so there's an interesting example. I had that, right, for this event, right, when you have the event as the output 6 and 6. So this is an independent event. Why? Look at the probability of E here. What is the probability of E? 6 and 6. 6 on red, 6 on blue. So there's only one case corresponding to that. And can you find out the probability of that? This is 1 by 36. Alright, now let's find out the let me call it S1 and S2. S1 is the case where the red dice is giving me 6, and S2 is the case where blue dice is giving me 6. Now what is the probability of S1 is equal to 1 by 6? Alright, so when you have one dice which is red in color and you want to get 6, so the probability is 1 by 6. What is probability of S2, which is getting a 6 when you're rolling a blue dice? That is 6 again. Alright, so now here probability of E is equal to 1 by 6 here multiplied by 1 by 6, which is 1 by 36. Therefore, by using this expression also you can prove that the event that the red dice getting a 6 and also the blue dice getting a 6 are independent of each other. And if you reason about it, yeah, it would be very, very intuitive. The number that you get on red dice is totally independent of the number that you get on the blue dice. Okay, so that's an example of independent event. Alright, so Bayes theorem. Alright, so now I know this is too much of a probability, but we have to live with it. These are two events, right? Event A and event B. Now let's try to find out some probabilities, like what is probability of A, what is the probability of B, what is the probability, the conditional probability of A given B, and also what is the conditional probability of B given A. So let's try to find out all these probability by doing it hard way, and then we will look at Bayes theorem and we'll try to see like how is Bayes theorem helping us in computing these probabilities. Alright, so this is a trick that I found online. So here is the link to the YouTube which I really enjoyed using when you have to solve the probability question involving pair of dice, and where the question is about what is the sum of the number that shows up on the dice. So what's the trick? The trick is to make a table like this, and here I have written these numbers in red because this signifies the number that shows up on the red dice, and here the numbers that you see are in blue because you know these are the numbers that shows up on the blue dice when you're rolling, and the number that is showing up on the top face. Alright, so what's the trick here? Well, if you have to solve the problem of the sum of the numbers on the top of the two dice, then you have 1, 2, 3, 4, 5, 6 for the 6 numbers that you will show up on the red dice, and 1 to 6 for the 6 number that will show up on the blue dice. Now when you have 1 on the red, 1 on the blue, then the sum is 2. When you have 1 on the red, 2 on the blue, sum is 3. Similarly, you know, keep on adding it. So 1 on the red, 3 on the blue, sum of the number is 4. Here 5, 6 and 7. So you can follow this logic and you can populate this table with the sum of the numbers which are showing up. So here you have 5 because 2 on the red, 3 on the blue. You have 6 because 2 on the red, 4 on the blue. Similarly, you will get till 8. Similarly, you will go to 9 because 3 red, 6 on 9, 8, so on and so forth. For 4 also you can find you can put these values like 4 plus 1, 5, 4 plus 2, 6, 4 plus 3, 7, 8, 9 and 10. Keep on doing it and you will get this table complete. 6 plus 6 is 12 and 6 plus 5 is 11, 10, 9, 8 and 7. Okay, so now whenever you are doing it, right, we want to keep an eye on what are our events. Event A says that at least one of the two dice be an even number, and event B says that the sum of the two dice is either 7 or 11. So this case B can be easily solved by making this table. Alright, so let's look at one event at a time. Event A says that at least one of the two dice be an even number. So now we are doing it in the difficult way, okay, but still we need to apply some logic. So when you're saying that at least one of the two dice should be an even number, then what is the trick? The trick that I tried was that, when you're saying that at least one of the two dice be an even number, what I will do is let me find out those cases where both the numbers that I am getting on dice red and blue happen to be odd, and let me throw those cases out. So that's my approach, elimination approach. So what did I do here? The number of here, my approach is that I will find out the total cases, total possibilities, and there are totally 36 possibilities, right? Combination 36, which you got in the sample space also. 6 multiplied by 6, so these are 36 entries. And these values that you see are the values of the random variables V. Okay, now out of these, my favorable cases are the total number minus total possibility, which is 36, minus those cases which do not satisfy my condition, minus the cases with both dices having the odd number. Now I should find out how many cases I have here where both of the dices are showing up odd number. So here you go, 1 1, 1 3, 1 5. So in the first row I had 3 such cases. Can I have that case in the second row? No, because here my first dice is 2. Doesn't matter what you get in the second dice. My first dice is 2, right? And what do I need? I need the condition that at least one of the two dice is even. Alright, and 2 is an even. Similarly, 4 is even, 6 is even. So I don't worry about what do I see on the second dice. I'm good. Okay, the only case where I should be careful is when my first dice is odd, right here. Okay, when my first dice is odd, then from the second dice I should make sure that it is even. So I kept this because the second one is even, first is odd. That this guy is even, first is odd. This guy is even, my one is odd. For 3 also I'll apply the same logic. 3 and 1 ruled out because both are odd. 3 2 is fine because this is what? This is even, right? This is even, so I'm keeping that. This is even, so I'm keeping that for this guy. Similarly, when you see 5 on the first dice, now you need to rule out the other odd ones. So you ruled out 1, you ruled out this 3, you ruled out this 5. Okay, so these highlighted red cells that I have are the ones that I will throw out. So how many of these I have? 3 plus 3 plus 3 plus 3 6 plus 3 9. So my favorable cases are 27. Okay, and the probability of A is equal to 27 divided by 36, which is 3 by 4. Was a little difficult, but not too complicated, right? We figured it out with the help of this trick. Let's move on. Alright, so with this animation I'm showing you, like, these are the favorable cases, and if you count these cells you'll get the same number, which is 27. Probability is 27 divided by 36, 3 by 4. Great. Now let's do the second part, the probability of the event B. Event B says that the sum of the two dice has to be 7 or 11. Now making this table helps, because the condition. The condition is that the sum should be 7 or 11. Just go and highlight those cells which are favorable. 7 here, 7 here, 7 here, right? So in this diagonal, if you look at, these are all 7. If you want to double check, 6 on the first dice, 1 on the second side dice. You add up, that is 7. 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. Alright, so these are 1, 2, 3, 4, 5, 6 cases that corresponds to sum as 7, and these are the 2 cases that corresponds to the sum being 11. So what's the probability? 6 plus 2, which is 8, divided by 36. Right, and you got the answer as 2 by 9. When you simplify, 4 2 times is 8, 4 9 times 36. Great. Now we will move on to more complicated stuff, which is conditional probability. We need to compute now the conditional probability of A given B. What was A? A is saying that at least one of the face that is showing up has to be even. What is the condition B? What is the event B? Event B says that the sum has to be either 7 or 11. And this is a very interesting case and which needs some thinking, right? So when you know the fact, right, what is the meaning of A given B? A given B, that means the conditional probability of A given that B has happened. And when B has happened means what? We already know that one of these event has happened. One of these 8 event has happened. And when will these 8 event happen? When can we get the sum as 7 or 11? Right? So the sum is odd. So when you're getting the sum as odd, then one of the number involved in that sum has to be an even. You're adding 2 numbers, right? When you add 2 numbers and the result is odd, then that means that one of the number is even. Okay, so the good news is that the probability is 1. Okay, so that's one way of thinking. The other way of thinking is, let's find out probability of A intersection B. What is A intersection B? All these 8 cases. Alright, all these 8 cases that you have are the cases for B and also for the cases for A. A needs that at least one of the face is even, and B needs that the sum of the faces is either 7 or 11. So you got that as 8 by 36. And what is the probability of B? The probability of B is also 8 by 36, which we found out right here. Alright, so what is the conditional probability of A given B? It's 1. Okay, good. So this was simpler. How about the conditional probability of B given A? Right, this is little interesting, but if you follow on this, we are following this expression that probability of conditional probability of A given B is the probability of A intersection B divided by probability of B. Now I just saw this typo. The capital B and the small b means the same thing. Alright, these are not different. Probability, this is also probability. It should be capital B. I'll fix that. Okay, and if not, then please don't get confused. Capital B and small b means the same thing, the probability. Alright, so let's move on. How will we compute the conditional probability of B given A? Let's use the same expression, which is probability of A intersection B divided by probability of A. Right? Okay. So we have probability of A intersection B, which is 8 by 36 divided by 27 by 36, and the result is 8 by 27. Probability of B given A. Okay, Alright, so now when you found all these things, this is what we were doing the hard way. Let's look at the Bayes theorem. Like, can Bayes theorem help us in doing this thing in simpler way? So the answer is yes. Why? Because we can use this expression, right? So probability of B given A we can compute if we know probability of A given B, probability of B, and probability of A. So we found the probability of conditional probability of A given B was 1, and we know the probability of B is 8 by 36, and we also know that probability of A is 27 by 36. Just put that in that expression and you'll get the result, which is the probability of B given A as 8 by 27. Alright. Okay, so what is this slide about? Well, this is about the probability distribution function, probability density function. Alright, so we also call that as PDF. So what do we show in probability density function? So this is based on our same example where we have two dice, one red, the other one is blue. We are rolling those two together and we are adding those numbers that show up on the top, and finding out the probability. And we have the notion of the random variable v, which has been defined. V is equal to sum of the numbers that it shows up. Now with that thing we can come up with this interesting plot. And what is this plot about? This plot will give you an idea about the probability of each random variable. So when random variable is 2, then this is the probability that we have. When it is 3, then that's the probability you get. When the random variable is 4, then that's the probability you have, right? So we can plot the probability value for each possible value of random variable. Random variable is taking value from 2 to 12, and we are finding out the probability corresponding to each value of the random variable. And when we do that, when we plot it in this way, what we get is probability density function. And how is that helpful? Well, if you have the probability density function, then you can use that to find out the probability. What you should be doing, go here, and that's the probability for the case where v is equal to 5. Alright, so you can use this plot to find out the probability corresponding to a random variable. Okay, so random variable has been already explained in the previous slide. Okay, now there's another thing which relates to probability density function, and this other thing is called cumulative distribution function. So this cumulative distribution is something which can be obtained from the probability density function, but the way we obtain this cumulative distribution function is slightly different, and here is the approach. And what is the cumulative distribution function? This in fact is the running sum of the probability density function. So what does that mean? So here you know that the probability of getting the 2 as the sum is right here. Okay, now when you came to this point here, you will add the probability of the previous random variable also. So the point is, how do we compute these values here, like k is equal to 4, then the cumulative value for x being less than or equal to 4 would be the sum of all these probabilities that you get till this point. You have to add all these numbers. Alright, so you keep on adding these numbers till this point. So when you are at 0.5, then at 5 what you should be doing, you need to add the probability that you have for v is equal to 2, for v is equal to 3, v is equal to 4, and then right here. Okay, so what's the significance of this cumulative distribution function? At times you are interested in finding out the probability of something happening with this condition. So if you are interested in finding out the probability of the v, which is the sum of the numbers being less than or equal to 5, okay, then right here you will get that value. Alright, so right here you will get this value, because that is how you are generating the cumulative distribution function. You are adding the numbers, that you obtained using the probability density function. Okay, so cumulative distribution function is the running sum of the probability density function. Right, so how did you obtain this curve? You obtained by adding these numbers. So right here you had the same value as you have here, but when you came to this point, you added these two values, right, and you got this. When you came here, you added all these three values. When you're here, you have added all these three values. When you're here, you added all these four values, and you keep on adding, and keep on adding. And that's the reason the plot that you have here for CDF is monotonically increasing. Right? It goes up, and up till it reaches 1. Probability cannot be more than 1. And at this point, what has happened? You have added all the probabilities. And when you add the probabilities of all the events, possible events, or the outcomes, the probability is 1. Okay, so please do this exercise. I did this exercise, and that's how I got these two curves. Alright, so interestingly, the probability density function will show a drop. It's not monotonically increasing. It goes up and then goes down. Whereas this guy keeps on going up, and up, because this is running sum. Alright, now often the people ask this question, like, which one is more informative? When you have a random variable and you are using that random variable to draw a probability density function or cumulative density function, then which one is more informative? So the answer is both the curve have the same information. Alright, so we cannot prefer one over the other. Interesting thing is that from cumulative distribution function you can get the PDF, and from PDF you can get the CDF. So in fact here we took the PDF to get the CDF. Okay, so this is very interesting actually. The only thing is that you need to have some patience, try to understand these expressions, take some example, work on it, and it will make sense. Excuse me. Now there's an interesting thing about the cumulative distribution and the PDF. So as I showed to you, and as is the case, that the CDF is monotonically increasing. That means it will increase, it will never go down. What happened was, in one of the briefing by the Apple CEO Tim Cook, he preferred to use the cumulative distribution to show that the Apple iPhone S sale is going up to the extent that it's exploding. Well, if you understand cumulative distribution, then it's no surprise. You'll catch this trick, because you know that cumulative distribution function will never go down, right? Whereas the probability distribution function will go down, and that will give you the true idea about what is going on. So this had happened, and you can find the reference right here. So although we have the reference of this thing in our textbook also, I googled it and find a reference right here. Okay, so if you want to know more about it, then you can go and read about it. So that's a trick people might use to deceive you. Okay, so yeah, so it's possible it might be what I say, exploited, right? But you should be smart enough to assess that this fact that cumulative distribution would always go up, so there's nothing great about it. The reality was that if you look at the reality, then this is cumulative distribution function, which will be monotonically increasing. But the reality was that the quarterly sales were not as exciting as was the cumulative sale. In fact, you can see that the quarterly sales went down. Okay, so cumulative distribution may at times be used to mislead people to show that if we have the increasing trend, but that may not be the case. Okay, so don't get deceived by cumulative distribution functions. If you see, it has a different purpose to serve. Okay, so in some cases it's very handy to use cumulative distribution function to answer questions on probability. All right, now we are moving to the statistics, right? Discussed a lot about probability. Let's see, like, what is statistics and when do we use statistics? So there's this descriptive statistics. Descriptive statistics will give some information about the data that we have. Okay, so again, now see the difference. When we were doing with probability, we were finding out the chances of something happening, right? We were finding out what is the probability of an event A happening when we already know that event B has happened. So conditional probability of A given B. So these kind of things we have done. In statistics, we deal with different kind of problems. We have a data set. Now we want to understand, like, what is the data set saying, right? So how can we describe this data set? So that's what descriptive statistics is all about. And before I get into the descriptive statistics, let's discuss something that we deal with. As an instructor, whenever I grade my test and make the test grades available, very soon the students they start asking me questions about statistics of the class. They are mostly interested in knowing what was the mean, what was the median, and they don't usually ask about standard deviation, but I provide that as well. And surprisingly, once I give them these measures, they are kind of satisfied. They have their own understanding. You people have some understanding, and you understand, like, how did the whole class perform. I don't tell you what was the maximum and minimum in most cases. You're happy with mean, median, and the standard deviation. The reason being that that is sufficient in most of the cases. Okay, so we will look at these basic descriptive statistics today. Now, when you have a data and you need to come up with the descriptive statistics, then there are two measures. One measure is called the central tendency, right? The central tendency measure, which will try to find out what's the center of the data that we have. Alright, so if you have the information about the center, then you will make a guess that that's the middle value, and the other values that I have in the data are centered around it. And this center value that you have, it could be either mean, which is the class average, or could be the median. We'll learn about median and mean pretty soon. So that's the central tendency measure. There's another thing which is called variation measure or variability measure. Now this variability measure is based on central tendency measure, and using variability measure you measure like how far the data is from the central of the data. How, or you can also say, how is this data spread around the center of the data. Okay, so these are two major descriptive statistics. Well, an example of a variation measure would be standard deviation and variance. Okay, so now how do we compute this mean? The simplest and most often used centrality measure is mean. which is average as well. So how do we compute that? It's pretty simple right here, right? Now, these notations might be a little scary. Well, we use mu as the symbol for the mean. So mu of x, that means the mean of the data which we are calling as x. And this x, you can think of x as an array if you like thinking in terms of programming. And the size is n, that means in this array I have n data elements. And how do you compute the mean? Just add every element and divide that by number of elements. Simplest possible. Now, there is an important information about mean. So mean is meaningful in the case where you have symmetric distribution, okay, and where you do not have outliers. Outlier means a value which is far away from the remaining values and values. So as an example, suppose that there are some 20 students in my class, and all the students, they scored in between 60 to 80, right? So I'll have some value of the mean, and I don't see any outlier if the students are scoring in the range from 60 to 80. Assume that I have one outlier in which the student scored 5, right? So I'll consider that as an outlier, because this 5, the value when you get 5, it will change my mean a little bit. Similarly, if I have somebody scoring 100, so that I can consider as an outlier, right? It's kind of away from the remaining values. Well, I have even more interesting case of outlier. So that was a mean, right? So but mean is susceptible to outlier, so that's something you need to keep in mind. You will prefer to use mean as the centrality measure when your distribution is symmetric and you don't have too many outliers. You don't have outliers. Let's get it that way. Now there are other centrality measures as well, like median. So median has an advantage. The advantage with the median is that it is not susceptible to outliers, okay, whereas the mean is susceptible to outliers. So we got mean, we got median. There's another interesting centrality measure which is called geometric mean. Now how do we find the geometric mean of n data values? Well, what you need to do is rather than adding these values, just multiply all these n values. So you do a1 multiplied by 2, a2, go on doing it for all the n elements, and then find the nth root of that. Okay, so now you might ask, like, okay, fine, that sounds interesting. Maybe theoretically, do we have any practical application of geometric mean? The answer to that is yes, right? And interestingly, geometric mean is used when you want to find, when you're dealing with averages. Alright, so if you have different averages, right, in your data set, data is about average, I'm sorry about that. It makes more sense when you have ratios. It's not average, I mean ratios. When your data is ratio data, and in the ratio data you're trying to find out the center, then for that you should use geometric mean. So the reason behind that is, assume that there's a tennis match going on. There are players A, B and C, and B is the reference player. A is half as strong as B, and C is 2 times as strong as B. A is half as strong as B, C is twice as strong as B. Now if you have to find out the average, then the average of half plus twice, if you do that I mean mean. When I'm saying average, that means mean. So when you do mean of 2.5, it will come out to be 1.25, I think, right? This is 2.5. You do 2.5 by 2, 1.25, which is kind of not so meaningful than if you do the geometric mean. Geometric mean of 1 by 2 into 2 by 1 raised to the power 1 by 2 is equal to 1. Okay, so when you're dealing with the ratios, when your data is ratio data, then in that case, geometric mean is more meaningful if you want to find out the centrality measure. Alright, so now the point is, which measure is best, right? So I'll say it all depends on the kind of data that you're handling. Mean is meaningful if you have symmetric distribution, and you don't have an outlier. And the cases where mean is best is when you're dealing with the data that has to deal with the heights of the people or weight of the people. Then this height and weight data is kind of a symmetric distribution. Alright, so which is centered around the mean. So for these cases where the distribution is supposed to be symmetric and you don't have outliers, I'll say you go with mean. Median is better when you have outlier and when the distribution is skewed. Alright, now an interesting thing which has been which is there in the textbook says that Bill Gates, who we should consider as an outlier because he is really rich, so if you add the worth of Bill Gates, or money that this guy has, and you compute the mean of the per capita wealth, right? So if you are computing mean per capita wealth including Bill Gates, then the value that you get is $250 more than what you will get when you take Bill Gates out. Alright, so that gives a very good idea about the fact that the mean is susceptible to outlier. Okay, so in that case, when you have somebody like Bill Gates in your data and you want to find out the per capita and the centrality measure for per capita wealth, you should use median in place of mean. Alright, so what is the aggregation? This is an interesting theoretical concept. So the point is that when a data is given to you, and then in place of reporting every data, you could report the statistics of the data, the descriptive statistics of the data, then that is often sufficient. Alright, and that results in the summarization of the data, the reduction of the data, right? As I cited, like for my students, if I just tell them that this is the mean, that's the median, and this is the standard deviation, and they may or may not ask, and if I also say that this is the max and this is the minimum of the score, probably they are happy with that. Okay, so in certain cases with this kind of statistics, we can achieve aggregation, right? We can use these derived features as the data value for some task, right? So aggregation as data reduction, so that will reduce the data. You don't need to send the whole data, just report the mean if you're taking mean, standard deviation, maximum, minimum, right? That's it for sometimes for dealing with a very huge data set. So this summary statistics is sufficient. Okay, and alright, so we have a few more slides left. So now let's look at the variance matrix. So till now we were just we have done the centrality measure. Let's look at the variance metric as well, so which will find out how spread the data is around the center. So one of the measure that we use very common is standard deviation. Now the point is, how do we compute standard deviation? The symbol that we use for that is sigma. So the standard deviation is basically the square root of the average of the square of the difference between every data point from its mean. Okay, so that's what it is. This sigma that you compute, which is standard deviation, is in fact the average, because you divide it by the number of data elements that you have. Here we are using n minus 1, and you're dividing by n minus 1, but what is the value? This value that you have in the numerator is summation from 1 to n. That means these many elements that you have, and you're finding out the difference of each element from the mean of the data, right? So in this way, what you're doing, you first compute the mean for the data, and then for every data that you have in the data set, find the difference of the data with the mean, square that and add those values, divide that by n minus 1 and compute the square root. Okay, so the square root, that's what we are doing. Now there's a difference. Sometimes people use n in the denominator, and in some cases they use n minus 1. Now the point is, when should you use n minus 1 and when should you use n? Now if your data set is really big, doesn't matter whether you're dividing by n or n minus 1, it will result in almost the same value. Now there's this notion of population standard deviation and sample standard deviation. So if you have the data about the population, that means you have all the data possible, right? Then you should divide by n. But if you're working on a sample of the data, you don't have the original data, right? So see, you want to find out the standard deviation for height of people in USA. Now if you happen to get the value of height for every individual in USA, then you should divide by n. But if by doing some sampling you were able to get the data for 10,000 people in USA, then what you should compute, you will compute the population, you will compute the sample standard deviation. So for sample standard deviation you should divide by n minus 1, but for population you should divide by n. Okay, so for sample you will divide by n minus 1. That's the only difference. Now this is an interesting case actually, and is discussed in our textbook. So the point is that sometimes it is possible to describe the distribution with the help of the centrality measure as well as the spread. Okay, so that gives a very good idea. So here we are looking at two probability distribution where the mean is same. So this is 3000, this is 3000, and in fact this data is about the life of two bulbs. One is a normal bulb on the left hand side, the other one is a bulb that you get in the print cartridge. So it's very interestingly discussed in our textbook. Now the normal bulb that you get will have the distribution like this. This is the distribution of the life of a bulb. So why is this distribution so even? Because that bulb that we have used in our day-to-day life has the equal probability of failing before the the mentioned life, which is 3000 hours. So it has equal probability of failing before 3000 hours of service, and it has equal probability of failing after those 3000 hours of service. But in some cases, like the bulb that we have in the print cartridge, they are manufactured in such a way that once they serve 3000 hours of service, after that they have to fail, right? So there is some notion of a counter, and the counter keeps counting like how many hours of service it has done, and after that automatically it fails. Alright, so the point is just that this mean may not give us all the information about distribution. The standard deviation is also important. Okay, and these two curves are different because here we have a different standard deviation. Here we have in fact very close to zero standard deviation. So mean as well as the standard deviation will tell us about the distribution. Just knowing one thing is not sufficient. So both these distributions have the same mean, but they look very different because their standard deviation is very different. Okay. Alright, so now I think this is our final slide, and this slide is about the distribution of the data once we know the mean and standard deviation. Now interestingly, this expression that you have, which I will explain, is applicable to all the distributions regardless of the fact that whether it is normal or some other distribution. So what does it say? It says that we have this expression which is 1 minus 1 by k squared. This fraction of data will be confined in the region between the mean and k sigma, k times sigma, right? So let me try creating a plot for you to give you some idea. I should use blue ink. So it says that if you have a distribution like this, right? So let me make this distribution. Here you have the mean. Alright, so with k is equal to 1 is not interesting, so let's take k is equal to 2. K is equal to 2. So k is equal to 2 means you have sigma here, you have 2 sigma here. What is sigma? Sigma means the standard deviation. You have 2 sigma here. Alright, right and left. So it should be minus 2 sigma because you're going on the left. It should be minus sigma. It should be positive sigma and 2 sigma. Now what it says is that when you have k is equal to 2, that means 1 minus 1 by 2 square, which is 3 by 4. Alright, 4 minus 1, 3 by 4. 3 by 4 into 100, which is 75%. Okay, so it says that in between this side 2 sigma, this side 2 sigma, if you have a distribution like this, right, maybe you have distribution like this, then the points that you have, okay, wait a second, let me erase this and then I will redraw this. I should not have redrawn everything. Anyway, sorry about that mess. Okay, let me draw that one more time. So you have this x-axis, here you have mean, right here you have 1 standard deviation, you have 2 standard deviation. Here you have 1 standard deviation, here minus 2 standard deviation. Alright, this is the mean. So it says that in between this and this, right, in between this and this, you have 75% of your distribution. So if it is something like this, right, sorry about this thing, then this region that you have, which is in between minus 2 sigma and 2 sigma, it will have 75% of the data. Alright, so that is a general result actually, which highlights the fact that your mean as well as the standard deviation are sufficient to tell about, you know, your distribution. Okay, and this is a general result. Alright, so I think I should stop right here, and I'll see you in the next video lecture. And I'm making an assumption, and probably that's the case, that you might have difficulty understanding these things. Please don't give up. Let me know if you have any questions in my office hours or through emails. Bye bye. Thank you.